Today, we want to try to reinforce the idea of partial derivatives and how we can visualize them. Derivatives themselves still work the same way they worked before. When we say the partial of z with respect to x, that's going to be the rate of change of z with respect to x. It's still a slope, the change in z divided by change in x. So rate of change of z with respect to x. And yesterday I phrased this a little bit differently. I said in the x direction. How is z changing in the x direction? And then Fy will be the same, but with y. So this is the rate of change of z with respect to y. And I phrased it a little bit differently yesterday. I said in the y direction. In this way, we're still thinking of it in terms of slope, delta z over delta x and delta z over delta y. It's just that the delta x is going in the x direction and the delta y is going in the y direction. We interpret the slope the same way that we always do. Delta z over delta x is approximately how much z will increase when x increases by 1. It's the change in z when x increases by 1. We usually divide it out to rise and run because we're all part of the anti-fraction faction. So we don't want to say z increases by 3 when x increases by 5. Or we want to say that instead of saying z increases by 3/5 when x increases by 1. We want to look at this in a little bit more detail. So let's come up with a function. So we know what this looks like already. And because it's in our slope-intercept style form, since it's solved for z, it's written as a function of z, we can see that dz dx is going to be 3. And since this is linear, we know this is going to be constant all over the place. It's always going to be 3. So I can just be all delta z over delta x. And then we can see this 2 is our rate of change of z with respect to y. So I'll say delta z over delta y is 2. When y increases by 1, z increases by 2. For delta z over delta x, if x increases by 1, z will increase by 3. We know what this looks like. This is a plane. It's going through the origin with these 2 slopes. Let's draw some contours of this plane. If you're thinking that I chose a plane because it's really easy to draw the contour, you are 100% correct. Because I can almost draw line segments. So, not trying to hide anything. Let's look at when z is equal to 0. We get the contour 3x plus 2y is equal to 0. Or y is equal to -3/2 x. Different values of z are just going to move these contours up and down. If z is equal to 2, I'm going to be dividing by 2, so I'm going to do even values of z. 3x plus 2y is equal to 2. We can see the slope right away by writing the lines, or writing the contours in function format. By writing y equals -3/x, then y equals -3/x plus 1. Notice we can see our change in z divided by the change in y. When z increases by 2, y has increased by 1. So we could see this in action. Here's our delta z of 2. And here is our delta y of 1. No surprises here. Harder to see in the x direction because I wrote in terms of y, but sometimes you just got to go with what's popular. And we can just keep following this. We don't even have to write stuff down anymore. We know that the plane, the contours of the plane are going to be parallel lines. So when I said draw some contours of this plane, you knew already that the contours would be parallel lines. Plane is in linear function in R3, not plane is in Y3. Although maybe if Tesla designs a cyberplane, it'll all be angles. I don't know why they designed the Cybertruck on like a Game Boy. Really kind of weird, but anyway. So we knew that the contours of the plane were going to be parallel lines. Here we can see they're parallel lines. They're going to be lines with a slope of -3/2. And we could see the delta z over delta y, the slope in the y direction in play. When z increased by 2, y is increased by 1. And that's constant all the way down because this is a plane and planes are easy. So we know what this looks like. It's a little dangerous. I'm not on the graph paper side of my, or the grid side of my paper. Oh, and I'm going to need some negative. I'm going to need more negative. I drew this upside down. See, it's because I keep forgetting to erase my notebook. So it's got all this other stuff on it. So here's a piece of a contour where z is equal. There's where z is equal to 0. This is just a piece of the contour. And then when z is equal to 2, have this parallel line. And when z is equal to 4, no surprises here. When z is equal to 6, the whole line just goes up one more. What we want to see is this delta z over delta y. We want to see the slope in the y direction. Let's go from one line to the other. If we go vertical, we can see here is y increasing by 1. And in that space, z increases by 2. So here's a delta y of 1. And between these two contours, delta z was equal to 2. Every time y increases by 1, z increases by 2. We can imagine that if we were walking along the y-axis, we can see ourselves going up this hill. We can see as we go up 1 unit in y, we've gone up 2 units in x. This is a very steep hill, so I hope you brought your height in. What we also want to look at, the delta z over delta x. What happens to z when x increases by 1? So I'm going to take this 3x plus 2y. I want to use that one. We also want to know what happens if x increases by 1. What happens to z? It's actually going a little bit past, because how much will z increase when x increases by 1? So notice that if this delta x is equal to 1, notice that line went a little farther. It went from 0 past 2, because when when x increases by 1, z increases by 3. So if x increases by 1, we'll be at the contour that has z is equal to 3. It's going to be in between the 2 and the 4. Because when we look at the equation of z is equal to 3x plus 2y. So the coefficient of x, when it's solved as a function, when it's written in z equals, that coefficient of x will be the change in z divided by the change in x. It's the slope in the x direction. And so if we see x increasing by 1, then z will increase by 3. And this is all proportional. If z increases by 2, then x will increase by, let's see, 2/3 of 3. 2 is 2/3 of 3. So x will have increased by 2/3. So similarly, because we just have to have a ratio of 3 to 1. So we can I also switched the order. That wasn't very good. That's kind of a jerk move on my part. Switch things around on you. Because we're dealing with a line, I'm gonna move this x down here. When x increases by 1, z increases by 3. These changes are always going to be in proportion. That's what flat functions do. That's what linear functions do. So if I drop my z change, I've divided my change in z by 3. That means I divide my change in x by 3. So if z increases by 2, like we see between these two lines, then that means X must have increased by 2/3. This is why we like lines. This is our default thinking. Our default thinking is always linear. This is why we go to the average all the time, even though the averages in most scenarios is trash. We add things up and divide by the number of things. We just go for the average. That's thinking linearly. It's the simplest way we could think of how things are changing. Let's take this z equals 2 contour. Grab the z equals 2 contour. That's the line y equals the z equals 2 contour is y equals -3/2 x plus 1, and find out where it hits the x-axis. The z equals 2 contour at the x-axis. So that means y equals 0. -3/2 x plus 1 equals 0. That tells us that -3/2 x is equal to -1. So that happens when x is equal to 2/3, just like we suspected. When x increases by 2/3, z will increase by 2. Any questions? When you're looking at partial derivatives at points, you're telling how to angle that plane in 2 different directions. You start with a flat plane and say the slope in the x direction is 3, so you crank that up to a 3, and the slope in the y direction is a 2, so you bend that up to 2. It's like one of those tables where the mark, you have like one controls the horizontal turns and the other one controls how the table is tilted vertically. It's like away from you, forward and backward. And then another control turns it right to left, and you have to make the marble go through. Does everybody know what that is? Or do we all just play Daisy? I brought up an Etch-a-Sketch a while ago. Yeah, it is. Because then, for a while, you could upgrade Etch-a-Sketch. You know that thing from Toy Story, but Toy Story is an old ass movie now. What year did Toy Story come out? Yeah. Anyway, what are we talking about? Oh, yes. Yes, it would be -1. Thank you. Now it looks like my equal sign has a giant mustache. So I drew this. Yeah. Here, let me make it. No, I don't understand children. Children are weird. I don't know how to deal with children. Michael, can you talk to them like normal adults? Because they're just small adults. People be like, oh, you can't use that language around children. Oh, incorrect. I just did. Obviously, sorry enough. Anyway. What I'm saying is if your children swear, you have reinforced that behavior. Somewhere that behavior has been reinforced, right? I learned a lot of these things from training dogs. Like if your dog has a certain behavior, Whether you like that behavior or not, that dog does that behavior because you reinforce that behavior. It's not trying, it doesn't have like motives or anything like that. You reinforce that behavior. That's the only reason the dog does it. Or the behavior itself is super reinforcing and you've let it go on too long. And so the behavior is very strongly reinforced. And it's your job to cope with it if you don't like it. Because if you just yell at the dog's just going to be afraid of you. And that's not what you want. You know what I mean? My dog counter surfs for like towels and stuff like that. So we didn't really stop that because when he started doing it, for one thing, it looks really funny when he jumps up on the counter and we're sitting on the couch in the living room. It looks like he's at the bar. He's like, oh, hey, what can I get you? And I say, I'll have a beer, my man. And he'll coming right up. And then he grabs me a towel. Then he'll come around the bar and say, I've got a towel. And I'm like, oh, motherfucker, you got a towel? He's like, oh, hell yeah. And then if I get up, he'll walk away because the game became reinforced that dad will give me some cheese in exchange for the towel. So he comes around the corner. He's like, oh, hey, I want to do some business. I got a towel. I would like to sell it for some cheese. I'm like, all right, let's trade. I'm like, oh, what do you want? 1 cheese or 2 cheese? You're like, oh, I would prefer 2. So I take 1 piece of cheese and I bite it in half and give them 2 pieces of cheese. Dogs can count, but they can't do fractions. So no dog is upset that you broke the cookie in half and gave them 2 cookies. Or gave them half a cookie because they're not like, oh, I just got half a cookie. They don't do fractions. They're like, oh, fuck yeah, I got 2 cookies out of that one. So, that's why whenever I'm like, oh man, people haven't done their homework because I've reinforced the behavior of not doing homework. I haven't created any consequence for not doing homework. I wait until the last day of class. Can I have an extension on the homework? Well, next semester, when you're doing this class over again, yeah. Dang it. What we want to do is visualize our partial derivatives, punctuation over. What we want to do is visualize our partial derivative. We're imagining a surface. Remember what the concept of calculus is. We want to find the equation of a line tangent to a curve that has morphed into plane tangent to a surface. And what we're thinking of, delta z over delta x, is how much that plane is tilted in the x direction. And then delta z over delta y is how much that plane is tilted in the y direction. So we maintain this and then we just kind of twist it along the y. We get these 2 different directions. Any questions? How's everybody okay? And also, since we talked about vectors, so our top view, we're thinking about delta z over delta x. And sorry, and dz dy. We have 2 different partial derivatives. So instead of just saying with respect to x, we might say in the x direction, because that's how it's tilted in the x direction. Okay. You can't see this on the video, but I did my hand gestures backwards. Normally I set that as the origin, which means this one is the x-axis and this one is the y-axis, and then this up and down. I went a little bit back. Glossy paper. Let's imagine that this is some contour of a surface. Why don't I always make my contours like linear at the point that I'm interested in? Right. We do. What color was DZBY? That was blue, right? I'm gonna make my contour green. I'm gonna try to make it curvier. Here's the point that I'm interested in. I'm gonna try to make this curvier. No, it's still kind of, it's fine. That's fine. Calm down. It's fine. So this is just one piece of a surface. Z equals f at x, y. I'll edit that out later. I totally won't edit it out later. So this is a contour of a surface, Z equals f at x, y. So there's some surface and it's got this weird curve in it. This is just one line. Remember, along this surface, this is where f of x, y is constant. This is a curve where z is constant. This is all a fixed value of z. So our function f at x, y is equal to some constant, k. I'll use the Morley constant. Now, at every point, we have a rate of change of z in the x direction, and we have a rate of change of z in the y direction. So at every point, we have like a dz dx and a dz dy. And at every point, we're always like one's horizontal and one's vertical. There's a dz dx and a dz dy. It looks like at this point up here, where it's kind of like at the top of a hill on this contour, I drew dz dy pointing directly up, but how much up is there at that point? If it's like right at the top of that hill, how much dz dy is there? 0. It's all dz dx, right? Over here, it looks like they're about the same. This is about going at a 45-degree angle, so the dz dx and the dz dy should be about the same, so that's not surprising. This one is a little bit weird because it's all dz dx. I'm just indicating the direction. But the two partial derivatives are just these two. How much in the x direction, how much in the y? What are our horizontal and vertical components of our direction? This is not new. This is what derivative tells us. Derivative tells us where things are headed, what direction we're going. We're just breaking it into two parts. What I want to do is look at this point here and think about what's going to happen. What should my derivative be in the direction tangent to the contour? So I want to put, imagine a direction tangent to the contour. So this is going to be a vector tangent to the contour. Oh, I can't use u. That becomes inappropriate really fast. So remember what we've got. We've got these are going to be our partial derivatives. This is going to be our partial derivative in the x direction And this is going to be our partial derivative in the y direction. But now I've got a vector tangent to the contour. Our vector is tangent to the contour. And I want to think about at that point, what is going to be the derivative in the direction of the vector tangent to the contour. This is what we want to think about. So the question is, how much is z going to change if we're moving tangent to the contour? How much does z change moving tangent to the contour? This is an evolution of our thinking. Our original idea about the derivative, how much y changes with respect to x? How much does y change in the x direction? Our fx and fy are two partial derivatives. Say, how much does z change in the x direction? How much does z change in the y direction? Those aren't the only two directions we have available in two-dimensional space. We can say, how much does z change if we go that way? And that way in this case is tangent to this contour. This is what I want you to think about. I want to figure out what f sub v is going to be. What is fv? This is why I had to switch from you. What is fv? The derivative of f tangent to the contour. Now, all I have to do is explain how this works. And all this stuff, like the gradient, all the rest of chapter 14 makes instant sense. And when we get into vector calculus, it's like, oh, yes, I remember now that one day where you talked about what the derivative in the direction tangent to the contour. When we calculated that and you explained that to us, it made everything snap into place and we instantly understood all of Calc 3. But if we want that to happen, I have to do that right now. So I'm going to explain right now this one thing that makes all of Calc 3 crystal clear instantly. But I have to do it right now. So here we go. Oh, dang, look at the time. It's not going to be enough time to do that. So that's going to do it for today. I guess we're going to have to go through Calc 3 at the normal rate. Some of you saw that coming and started packing up as soon as I started talking about that. That's going to do it for today. I'll see y'all on tomorrow. Think about this problem, not actively, just let it sit in the back of your mind and then be reminded of it tomorrow, because this is what we open with tomorrow. That's it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.